Good. So now we know that. We know that there are two very important exponential functions, one with a base e, natural exponential function, and the other one with base 10, common exponential function. You've noticed that they have special keys on the graphing calculator. They are in blue. In other words, they are not the first function on that key. The first function will be their inverse. Okay, so we'll get to that. So let's graph the other shape. So let's look at the function that is exponential, but now it has, so this was a base greater than 1. 2 is greater than 1, e is greater than 1, 10 is greater than 1. So now we want to look at the exponential function with a tiny base. Let's say 1/2 raised to the x power. So notice that when the base is greater than 1, the function is increasing everywhere from negative infinity to positive infinity. It continues to increase. Okay? Good. So now let's identify the domain of this function. What is the domain of f of x 1/2 to the x? This is a friendly function, no problems whatsoever. So the domain is all real numbers. We will pick the same values like we did before with the base 2, greater than 1, -2, -1, 0, 1, and 2. And we want to determine those values. So let's determine 1/2 raised to -2. 1/2 raised to -2. So f of -2 equals 1/2 raised to -2. I would love to replace this by something. What can I replace 1/2 by? Another notation is 2 raised to -1. 2 raised to -1 is 1/2. So I copy the base. What happens to the exponents? I'm raising to a power. So we copy the base, and when we raise to a power, exactly. So this is 4. 1/2 raised to -1. In the same way, 1/2 raised to -1 will be yes, awesome. Because it's 2 to -1 raised to -1, and I multiply. Excellent. 1/2 raised to 0. And this is valid for any number raised to 0 except 0. Thank you. At least we know where to look. And then 1/2 raised to the first power is obviously, and 1/2 raised to the second power is 1/2 times 1/2. Yes. Let's see where we're going this way. 4, 2, 1, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, 1/1,000,000. Where am I going? Yes. And towards what? Excellent. Cannot be negative. Awesome. Now going this the other direction. 1, 2, 4, 8, 16, 32, 64. Where am I going? Excellent. So let's graph this function now. Good. So from left to right, please give me the first ordered pair. Very good. So -2, 4. Perfect. That's our first point. Next ordered pair. Excellent. Next ordered pair. Perfect. Next one. Good. Yep, that's more and more difficult. Okay, here it is. It doesn't touch the x-axis. It will eventually get closer and closer. And this is 1/2 raised to x. What is the difference between the base greater than 1 and the base less than 1? The base greater than 1 does this all the time, and the base less than 1 does this. What does that mean? Always? Always decreasing. It's an always decreasing function. Yes. Smaller and smaller and smaller and smaller. This is the fastest increase possible. Good. So now, is this function 1-to-1? By the horizontal line test, is this function 1-to-1? Yes. So it has an inverse. Awesome. So let's graph the inverse. I graph y equals x first, because I know the two functions will be symmetric with respect to this line. And I would like to get some points, so I can graph. Awesome.
I'm sorry, 2 and -1.
Correct.
1 and 0.
Correct.
1/2 and 1.
Very good.
And 2.
Okay. Notice one thing. Where the first function crosses, x and y are the same. So when I reverse them for the other function, the function has, the inverse function has to cross at the same point. Because y and x are the same, and when I reverse the point, I get the same point. 4, reverse, still 4. This is the inverse function of function 1/2 to the x. Notice that the inverse function is also decreasing. So if the function, the exponential function is increasing, its inverse will be increasing. If the exponential function is decreasing, its inverse will also be decreasing. I would like to look at some word problems, a couple of them, and then equations. These are the easiest possible word problems. Let's say 40 on page 736. Let's read it. Retail revenue from shopping on the internet is currently growing at a rate of 26% per year. In 2003, a total of $39 billion in revenue was collected through internet retail sales. Answer the following questions using y, of course, or f of t, the same thing, 39 multiplied by 1.26 raised to power t, where y is the internet revenue in billions of dollars. Internet revenue and t is the number of years after 2003. T, number of years after 2003. According to the model, it's the first question now. According to the model, what level of retail revenues from internet shopping was expected in 2005? What does that mean? What do I have to do?
2 and 13.
Exactly. This represents t equals 2 because this represents t equals 0. Awesome. So all I have to do is find f of 2. Leave it alone because we cannot do it by hand, and we'll do it with the graphing calculator in a second. Part B. If the given model continues to be valid, predict the level of internet shopping revenues in 2015.
After 12.
Yes. So f of 12. So here's what I would like us to do. Back to our calculators. I would like to put this function in y equals. So let's go to y equals right here. And clear if you'd like, clear everything that you had from before. And the function is 39. Is it 39 or 3.9? No, 39, correct. So 39 in parentheses, 1.26, close the parenthesis, put the power caret x. We don't have t in the calculator. We have to use x. But that's okay. Now go back to second and table set. Let me know if you need help. Do we see this? Scroll down and change the independent variable in ask. So scroll down and then could go to the right, highlight ask, and press enter. Just the independent variable. Are we okay? Now we go to second and table. Second again and table. Again, what do we want to plug in x? What did we say?
2.
We want to plug in 2 and press enter. And we want to plug in 12 and press enter. Okay, so how many billion of dollars in 2005?
61.916.
Yes. Okay, what about 12?
624.47.
That's it. So we didn't have to put the calculate or create the calculation twice. We created the function, we put the function in y equals, and we used the table to plug in what we wanted. That's it. That's the whole world problem. Happy? Good. Okay, so let's look at some equations. Oh, actually, I want to do one more type. On page 737, before we look at equations. We're given the following formula, and it will be given to you. What does each variable represent? N is the number of times interest is compounded. Recalculated, that's what it means. R, annual interest rate. P is the principal. What we deposit in a bank account or what I borrow from you. I borrowed money from you. That's the principal. A is the accumulated value. If I deposit the principal, then the accumulated value will give me the amount 10 years from now. If I borrow the principal from you, then in 10 years from now, this formula will calculate how much I have to give you back. And T is time in years. Okay? Find the amount Erica owes at the end of 3 years. So this is problem 47. So time equals 3 years. If $6,000 is loaned to her, is this the accumulated value or the principal? Of course. So $6,000 was loaned to her at a rate of 8%. What is that? 0.08, very good. I cannot use percentages. Compounded monthly. How much is N for compounded monthly? How many months are in a year? 12. Good. So please dictate how much she owes at the end of 3 years. You will say A equals, what do I write?
6,000.
Correct? Yes?
1 plus 0.08 over 12 parentheses exponent 12 times 3.
That's it. That's it. We can't do anything. We have to do it with a calculator. So get out of there with second and quit. The quit button is right next to second. Second and quit. So 6,000. Parentheses. 1 plus 0.08 divided by 12. Close the parenthesis. Put the caret. Put parentheses again if you don't want to multiply. And just write 12 times 3. If you want to multiply and say 36, you don't need parentheses. But I recommend it. So she borrows $6,000 today. How much money she has to give back in 3 years? That's it. That's how the formula works. Okay, one more. 50. Find the amount accrued. If 500, what does 500 represent? Is invested, of course, and earned 7%, of course, per year, or 0.07, compounded monthly again. Good. And for 4 years. Good. So I will have now how much money we make on 500. So that will be 500 in parentheses 1 plus 0.07 over 12 raised to power 12 multiplied by 4. No one can do this by hand. So 500 parentheses 1 plus 0.07 divided by 12. Don't forget the caret. Don't forget parentheses. 12 times 4, unless you put 48. Multiply by 4, close the parenthesis, and press enter. So we will make in 4 years at 7% per year. If we deposit $500 today, we will end up having a total of 661.03. Yep. Very good. Clear? Okay. Exponential function is not difficult. It may sound at the beginning scary because of those two shapes, the base this, base that, but it's not difficult to work with. Okay, last topic in this section, exponential equations. In radical equations, the variable is under a radical. In absolute value equations, the variable is in absolute value. Now, in exponential equations, the variable is the exponent. Awesome. Okay, on page 736, these problems are between 21 and 36. Yes, 21 and 36. Okay, I'm going to start. You can pick if you want. I'm going to start with 25. 32 raised to 2x minus 3 equals 2. Before, is this an exponential equation?
Yeah.
Yes, because the variable is the exponent. Very good. Now, before we even look at this problem, I like to look at this. 3 raised to the x equals 3 raised to the 4th power. This number, I am told, equals this number. And they're both exponentials, right? This is an exponential function. This is a number. But I see the same base. What could this number be? Absolutely. There is no other way. It's 1 to 1, right? I can't find two numbers, two powers of 3 that will give us 3 to the 4th, right? So x must be 4. This is the idea I have to use here. There is nothing I can do to 2. but there is something I can do to 32 in the hope that I can write it with the same base. If I cannot write these two numbers like here with the same base, I will not be able to solve in this class. I have to wait for the next one. So I could have the possibility of this. 2 to the x equals 3. We cannot solve this equation in this class. Both sides have to have the same base. Okay. No, I want to change 32 into an exponent, an exponential notation, with the base 2, because I have to have the same base on both sides. And so there is only one way of rewriting 32 with base 2. 2 raised to the excellent. So 32 was replaced by 2 to the 5th. Now, the left-hand side needs to be simplified. I copy the base. What happens with the exponents? We just did this when we graphed the other shape. Exactly. So I have to distribute 5 to 2x and 5 to negative 3. What do I get? Equals 2. Awesome. Now I have two numbers with the same base. What has to happen to their exponents for them to be equal indeed? Right. In other words, the exponent of this, which is 10x minus 15, must equal the exponent of this, which is exactly. That's how we solve exponential equations of this type. I will move that now this is linear. I will move 15, so I have 10x equals 16, and then I divide by 10. So x equals 16 over 10, and I simplify. X equals 8 divided by 5. Any questions? I know we need examples. So let's look at 35. 81 raised to x minus 1 equals 27 raised to 2x. What type of equation is this? Good. Well, 81 and 27, if I can present them with the same base, and the bases should always be prime numbers, not 4, not 6, something like that. Either 2 or 3 or 5 or 7, okay? If I can present both sides with the same base, then I don't know how to solve it in this class. So what can I do to 81? I need to replace 81 by something raised to a power. Right? That's true. However, 9 is not a prime number. Awesome. You're on the right track. And 9 will be presented how? Exactly. 3 to the 9 and 9. So 2 threes in 1 9 and 2 more threes. So no, 2 and 2, right?
Yeah.
So it's 3 to the 4th. Everything raised to x minus 1. Good. Now the race is against 3. Can I use 3 as a base for 27? If I can, I'm on the right track. I can solve this.
Yes.
How?
3 to the 3rd.
Excellent. It looks very promising. So on the left-hand side, I copy the base. What happens with the exponents? Right. What do I get?
4x minus 4.
Awesome. On the right-hand side, I copy the base. What happens with the exponents? Good.
6x.
Awesome. So now I have two. I'm not simplifying or anything. So in the past, I saw students, they will cross this 3 out and they will cross. No. We're not doing that. We're saying this. Two numbers are equal and they have the same base. what has to happen for them. Right. In other words, 4x minus 4 equals 6x. We're not simplifying the bases. Awesome. Well, this is a linear equation. I know what to do. I subtract 4x. I get negative 4 equals 2x. Therefore, x equals, that's it. Okay, let's work on one more and move on. We can come back. We'll come back when we continue with the review. So let's say 34. 125 raised to x minus 2 equals 25. So what do we do with to 125?
Becomes 5 to the third.
Awesome. 5 to the third, everything to x minus 2. What do we do to the right-hand side?
Becomes 5 squared.
Awesome. So then I copy the base, and what happens with the exponents?
Becomes 3x minus 6.
Very good. 3x minus 6 equals 5 squared. So now here's the idea. Two numbers are equal, and they have the same base. Therefore,
3x minus 6 equals 2.
so then 3x equals 8, x equals 8 over 3.
Then another one with the base isn't the same.
No,
Okay.
not in this class.
Okay.
We can have that, and we can determine them, yes, but not in this class. This is part of the next class, that type of exponential. Do we need more examples, or can we move on? Okay, so now 12.5, logarithmic functions. So let's try to understand the mechanism behind log functions and what they are. Let's pick an exponential function, one of the two that we already looked at. Oh, actually, we looked at 3 exponentials plus the decreasing one. Well, let's say 2 to the x. So let's say the function is 2 to the x, and I'm going to pick some values here. I'm going to pick 0, I'm going to pick negative 2, and I'm going to pick 3. Now, 0 will correspond to what? So if I put 0 in here, 2 raised to 0 will be perfect. If I put negative 2, then 2 raised to negative 2 will be so 2 raised to negative 2 is 1 over 2 squared. Because the power is negative, it brings it down. Yes, but 1/4, because it's negative 2. Okay, and the last one, when x is 3, what do we get? Excellent. Good. If you remember, how do we create the inverse function? We develop a function, we create a function that takes all these values back where they came from. And this will be denoted by f inverse, right? So what will f inverse do? F inverse will be applied to 1, and the result must be, perfect. F inverse will be applied to 1/4, and the result must be, because we reversed the coordinates, right? And F inverse has to be applied to 8, and it will return 3. Okay, I will show you how we do that, and indeed, it works. Okay, the notation, how we denote this, is this, from the log function. Log, the base must be the same. What base? What is the same? Which base would I have to have in log? Which base we see here? Exactly, it has to be the same base. Base 2, and it's written right here at the bottom of the tail of G of x. So this is how we read this function. Log base 2 of x. And now you should say, show me. Show me that when you apply log base 2 to 1, you get 0. Show me that when you apply log base 2 to 1/4, you get -2. And when you apply log base 2 to 8, you get 3. And this is what I'm going to do next. I'm going to show that to you. The most important concept in chapter 12. And this is by me. Other people may not consider that, so I'm going to just say here by me. Is this: any exponential equation can be replaced by a log equation, comma, and vice versa. And this is in plain English. We're going to come up with mathematical notation in a minute. So any exponential equation can be replaced by a log equation, and any log equation can be replaced by an exponential equation. How come? Okay, here's the procedure. Log base A of x is a number y. This is my log equation. I'm using this symbol. This is the double equivalency symbol. What does this symbol mean? It means that this can be changed into this, and this can be changed into this. I didn't write the right-hand side yet. So let's do this together so we remember this. So how do I change this log equation into an exponential equation? I always start with the base, and I go counterclockwise. The base raised to this number equals x. The base raised to this number equals x. And now you can say, wait a minute, this is very interesting, but you're telling us that you're going to show that log base 2 applied to 1 is 0, log base 2 applied to 1/4 is -2, and log base 2 applied to 8 equals 3. I cannot show you unless I show you this first. Okay? So then, now I'm ready to show you. So I'm going to apply log base 2 to 1. Well, let's see what happens. I'm here. I'm just mimicking the left-hand side. Log base 2 of 1 is a number y. I have no idea what it is, but this is definitely equivalent to, and please tell me what to write. 2 raised to y equals 2 raised to only one number will ever give us 1. Which number is that? Exactly. Therefore, y is 0. So I'm coming back to my little bubbles here. Can I say that we indeed concluded that log base 2 of 1 returns 0? Now I will look at log base 2 of, that's it. I mimic the same, the left-hand side. Log base 2 of 1/4, I have no clue. It's a number y. I don't know what that is, but I know that this can be replaced by an exponential equation. So please give me the exponential equation that replaces this log equation. Good. But as we studied a few minutes ago, I have to present both sides with the same base in order to figure out or solve the equation. The left-hand side I cannot do anything to, but the right-hand side has to be presented with the same base. How do I do that?
Y equals 1. But the exponents have to be the same. Oh, no.
No, the base.
Oh, so you're multiplying by 8.
So 1/4 has to be presented with base 2. 2 raised to what power is 1/4? First of all, it has to be a negative number. Exactly. Now I can clearly say what is y. How much? Okay, so let's go back to our bubbles. Is that clear that when we apply log base 2 to 1/4, we get -2? Awesome. Good, one more. We apply now log base 2 to what?
8.
Perfect. I have no idea what this is. But I know that I can change it into an exponential equation that I know how to solve. What will that be? Good. Again, both sides have to have the same base, otherwise I can't solve. So the left-hand side is 2 to y. How do I rewrite the right-hand side? Exactly. Therefore, I know how much is y. What can it be? Only 3. And then going back, I hope we are convinced now that when we apply log base 2 to 8, the number that we get back is 3. Therefore, this function is the inverse of that function. Now, we looked at 2 more functions and we graphed them when my computer crashed. What were those other 2 functions, exponential ones? And their names. Good, which is e to the x. Good. And 10 to the x. Awesome. Okay. They have inverses, and they are log. So this one has the inverse function, this one. No number here. I know it's base 10. And this one has the inverse function. It should be log base e, but it's denoted by ln. And of course, they bear pretty similar names. This is the natural log function. And this is the common log function. They're so important. If you remember, they have a special key right here. Log is together with 10 to the x. Ln is together with e to the x. They are inverses of each other. So 10 to the x, log e to the x, ln. Okay? Good. So now I would like to look at all sorts of different equations on page 749. Write each as an exponential equation. Okay, so let's look at 8. No, I'm sorry. I'm sorry. Thank you. Log base 8 of y is 7. Please give me the exponential equation. We are not asked to solve. We are not asked to do anything. Just write each as an exponential equation. That's it. 15. Log base 3 of 1 over 81 equals negative 4. That's it. And it's true, because this is 1 over 3 to the 4th, right? Good. Let's go backwards. Write each as a log equation. So let's say 20. So I'm going to write it here on this side. 10 to the 4th equals 10,000. Going backwards from an exponential to a log is slightly more difficult, but it doesn't have to be if you follow this. So you have the right-hand side, and the left-hand side has to have a log. I have to have a number here. I have to have a number here, and I have to have a number here. You don't have to use my symbols, of course. So what will this be? Of course. What will this be? Indeed. And what can this be? That's it. So now you can rewrite log, because base 10 by convention we don't write. 10,000. So common log 10,000 is 4. As long as you keep it in the same order, you will never make a mistake. Uh, 25. In 25, we have 4. Oops, I didn't want to write it there. 4 raised to negative 2 equals 1 over 16. Always write the log. You know you have to come up with 3 numbers. The equal symbol. So I have log. I have something here, the equal symbol, and something here. Always start in the same order. Always start with the base. Right? Of course, there is nothing else. That's it. Pi raised to the 5th equals y. We just talked about pi. Ready? We're asked to write the log. So I have log, something here, the equal symbol, something here. Always start with the base. Always move to the right. Right? Pi raised to the 5th power equals y. Okay, so now it says find the value of each log expression. Fine. So 32. log base 2 of 1 over 32. I have no clue what this is. I'm going to say this is y, but I know that this can be replaced by an exponential equation, and that's what I'm after. Which exponential equation? Exactly. Very good. I know how to solve this as long as the other side has the same base with what? What base? 2. Very good. So 2 to y equals 2 raised to blah, blah, blah. Raised to what? It's a fraction, so then the power must be negative. Exactly. So then how much is y? That's it. In other words, log base 2 of 1 over 32 is? That's it. That's the answer. Good. Let's take a look. 37. Log base 6 of 1. I have no clue. This must be y. And let's look at changing it into an exponential. How do I change this into an exponential? Good. Now let's think. What could y be? There is no other way. Okay. 41. Log base 3 of 81. I have no clue, but I know how to change this into an exponential equation. How do I do that? I will be able to solve easily if, and only if, 81 is written. There are 2 9s, right? Each 9 has 2 3s. 4. Therefore, y must be 4. Did we get the idea? Okay, let's also look at 57. Log base 4 of 16, they say it's x. Fine. We're asked to find x. Awesome. Now you could, I highly recommend prime numbers, but in this case you could keep 4 to the x because the right-hand side is, that's it. Therefore, x must be 2. Okay, let's look at one more, like 60. Log, this time the base is 2/3 x of x equals 2. Yes. 2/3, everything squared, everything, equals x. Awesome. So then x is, how do we square a fraction? We square the top and we square the bottom, or 2 over 3 times 2 over 3, right? What do I get? Square 2. Square 3.
Oh, 9. I was times into.
It sounded right when it came out.
Good. So we continue in the same thing. This is the last section, 12.7. Same rules, everything the same, more equations. So let's take a look. Page 762. Use a calculator to approximate each log. So we're going to look at 6. We want to approximate natural log 2. And at 10, approximate log, common log of 25.9. So let's take a look. So the graphing calculator went to approximate natural log 2. So click on natural log, put 2, close the parenthesis, and press enter. Then approximating log, common log of 25.9. 25.9, close the parenthesis, and that's 1.41. So natural log 2, 0.6931, and 1.4132. Okay, so before we look at few equations, I like to find the exact value. Same thing, same idea. Okay, so let's say 26. Natural log e raised to -5. How much? Don't forget parentheses. That's it. Good. Let's say 30. Log of the square root of 10. Very good. Good. So let's look at a couple of equations from the same page. (38) Natural log x equals 2.1. I have no clue. But I know that every log equation can be replaced by. Good. But now I have to remember what is the base for this ln. If I forget, I look at the calculator and they are paired on the same key. E. So this is e raised to which power? Right. Equals x. All I have to do is plug it in the graphing calculator and find it out. Find out what it is. So here's your, so I want to show you two things. If you only want e with no power, you will be using this. Second and e. E with no power. But that's not what I want. I want this one right here. So second and natural log, you will pop up with the power, and I want the power to be 2.1. And press enter. So 8.166. Is that okay? 45. Log 2x plus 1 equals -0.5. Oh, sorry. I have no clue, but I know how to change it. Into what? Yes. Yes, exactly. Now this is linear. What do I have to do to find x? Move the 1 and divide by 2. Awesome. So 10 to negative 0.5 minus 1 divided by 2 will be x. Let's punch it in. Please put parentheses around the numerator in the calculator. Put 10 caret in parentheses negative 0.5. We use this negative at the bottom. Close the parenthesis. Go outside of that and minus 1. Close the parenthesis for the numerator and divide by 2. And that is the answer. Negative 0.34188. Approximately. Negative 0.34189 if you want.
Yeah, how come when we put that in the calculator, we had to put the negative 0.5 in parentheses as well?
Because it's a power. I recommend it. Yes, I recommend with the power. Now, I would like to check this. I want to put it back in here with log in parentheses 2, previous answer, plus 1, see if it's negative 0.05. Okay, ready? So I will write log. I will click on log. Then I have 2. I don't want to approximate. I'm going to say multiplied. I don't want to approximate. I go to second and the previous answer. I want the calculator to take it all. I don't want to truncate this number. I want to use the whole thing. And then plus 1, and close the parenthesis. When I hit enter, what should I get? If my answer is correct, what should I get? Correct. So press enter and get negative 0.5. Any questions?